So today we are pleased to welcome Professor Javier Cancela and Professor Jorge Dafonte from the University of Santiago de Compostela in the north of Spain. Javier Cancela is a professor with expertise and experience in irrigation engineering, agricultural water management, and sustainable irrigation systems, and he also serves as Vice President of the Spanish Association of Irrigation and Drainage. And Jorge Dafonte is also a professor at the University of Santiago de Compostela with a background linked to engineering and technological application in agriculture. It is a pleasure to have both of them with us today. So the floor is yours.
Thank you, Miguel. Sorry for this little delay. Only a moment that now it's okay. To avoid double sound. As mentioned by Miguel Angel, we stay here to present two parts in this session about our research. The first part is related with a project that we have on course today, actually, this year. And then at the end of the presentation, at the meeting of the presentation, my colleague Jorge Dafonte present for you the another part related with the low-cost sensor. In my case, please, Jorge, next. If you can pass to the next, please. Thanks. Thank you. The subject that we are to present today is related with this European project. It's a pseudo project that are related with the south of France, Portugal, and Spain. The project is the project IrriWater. It's a project related with the management of reclaimed water and their use in the irrigated agriculture. Next, Jorge, please. The main objective of the project is that you can read perfectly is try to increase the use of reclaimed water in the irrigated crops and show how is the best option, how to manage, how are the possible difficulties, the advantage and disadvantage. And at the end, obviously, we will try to define a transnational strategy to implement this document in the different entities that could be interesting in relation to the reclaimed water, some related with administration, companies, irrigation, communities, and final users, obviously. Next. We have three main objectives. This mentioned previously transnational strategy. And then we have two other main specific objectives. The second is the development of different pilot actions related to apply reclaimed water to irrigate, obviously, horticultural crops and woody crops. And that I can show you in the next slides. And finally, we have a third main specific objective that is the development of the hub IrriWater. It's a hub that have all information, basic and technical, and more complex information related with the reclaimed water in the actual state in Europe. Next. Our consortium have 16 entities. You can see the names of the left of the slide. We have not only research and universities, we have other entities as a Foundation Juana de Vega, Amaya, that is other entity at regional level in Andalusia. Then we have a very nice and very interesting associate members that Area Metropolitana de Barcelona that are involved with all the surrounding of the Barcelona city. Small companies as Hope in Terre du Blanc in France, water management entities as Gestagua or Augas do Norte in Portugal. And finally, we have the collaboration of the government of Andorra. Next. Moreover, we have 39 associate entities. It's crazy, I know. As you can see, sometimes I forget the name of the quality of the entities. As you can see, we have everybody that you can show in this slide involved with the project to divulgation, transfer information, to collaborate with the definition of the national strategy in different levels of collaboration. You can see here, for example, the different Ministry of Spain, different Confederaciones Hidrográficas, that is the entity that regulates the water management in general in the regions in Spain. Then we have several wineries in Portugal, Esporão, Quinta do Canhoto. Then we have two different confederations and associations, local governments as Concello de Lugo, many different association entities as ADBID, related with the vineyard, or Asociación Portuguesa dos Recursos Hídricos, and so other that you can see with detail in these slides. Next. Well, one of the first questions that we have developed is this document that you could read in detail in this link. I think so that the presentation is available to everybody. For the reason I don't stop here no more than only to explain that this is a starting point of the actual situation in the use of reclaimed water related with the agriculture in the European region, but specifically in the countries that are involved in the Sudo area, that is Portugal, Spain, France, and Andorra. I recommend that you review this document. It's open to everybody. Next. We are developing this transnational strategy using information. As you can see in this image, you can see the wastewater treatment plant points in the three countries involved, and we are trying to relate information about the population of this wastewater treatment plant, the technology, the location, and the altitude of these plants in relation with the irrigation community perimeters that we have in the three countries. With this information, we are working to develop a tool that could to the user select what is the wastewater treatment plant that is near of this of the field plot that the people who want to irrigate, and try to relate the possibility about the resources and the demand that the final user has. This task is encouraged by the company Gestagua. Next, please. Well, the next objective, pilot action. As you can see in the map of the right, where you could see the location of the different action pilots. We have different crops, body crops, a vineyard. We have in total 5 pilot actions. In relation to hop, Humulus lupulus, that is one of the key raw materials to the beer. We have 4. In relation to almond, we have other 2 pilot actions, and in relation to olive, other 2. More or less, the distribution is exactly that you can see in the image. And then, in different way, due to the in relation with the contact of the reclaimed water with the final products, we have other 2 very interesting action pilots, that is in tomato and in watermelon, because the quality of the water, of the reclaimed water, is different at legal level. Next, please. Well, in this case, we are developing different equipment to monitoring the water, but always the fertigation. We can mention that the reclaimed water is not only water. This water have a lot of a small or not a small quantity of nitrogen and phosphorus, for example. We have developed several equipments that Jorge explained in the second part of the presentation. And then we will try to take different measures about the crop physiology, yield, quality of the all crops that I have mentioned in the previous slide. Next. Obviously, all information related with the data are involved a partner that is UTAF in north of Portugal with a platform that the name is MySense. You can see here one example of the information that we can see. For example, we have here the electrical conductivity using the Tirus 12 sensor or the raw data of the soil water content, how is modifying the values along of the week or month. In this case, is the December or sorry January in past year. Next. Other question that I have not mentioned previously is that in our project IrriWater, we are developing a decision support system to try to help to the final user to manage this reclaimed water, mainly in relation about the fertigation or the nutrition that the crops required. In this case, several partners are involved: University of Córdoba, IRTA, Oficina del Regante in Catalonia, and UTAF in north of Portugal, using different platforms previously developed by these beneficiaries. For example, Redex, Reutivar, and MySense that you can see previously, to try to obtain a simplified tool to help the user to know what is the quantity of nutrients that I have pending to apply to my crop to obtain the best final solution. Okay, next. This is the last summary in a schematic image of the last specific objective, that is a hub. In this hub, we are taking into account all different key aspects in relation with the reclaimed water in agriculture, in the sector of agriculture in general, not only irrigation. We were trying to include information about the agro-industry and how is the possibilities or what are the possibilities in the agro-industry to use reclaimed water, including basic information, legal information, socio-economic information, the risk plan management detail, and we were trying to include information about how is the process to obtain a legal point to use reclaimed water and something like that. And moreover, all people have the option to connect to this hub, download information, interact with the previous tool that I showed, the decision support system, and try to interact with the research available, or the potential research available, and the distance from one point of the area to the irrigation perimeter, and so on. For the reason, I invite to everybody to visit our hut. It's not available right now, but in 3 months, we can share with you this link and invite it to everybody. Next. Only 2 final remarks about the pilot action and decision support system to fertigation. We think that is a very interesting tool to share with everybody. Obviously, in this type of European project, we are very interested in have your feedback about your knowledge or your question about reclaimed water in irrigated crops, in our case. For this reason, we are open to receive your comment questions about it. And finally, one question that is very relevant too is this transnational strategy that we are developing, that we need try to integrate all governance levels, local, regional, national, European, but all but we are trying to involve to the citizens, all citizens. For example, we have make different taste beer, experimental beers using reclaimed water to produce beer, and all people, many people are involved to try to test this beer and to know the difference and something like that. For this reason, we are open not only to the governance level, all or we have included to the citizen participation. And finally, we are open. We have finished really the participatory process using a survey to the different levels of governance involved in this type of in the strategy that we are preparing. And that's all for me. I think so. I have other slides. I remember. Please, Jorge, next. Yeah, this is only a question that may be relevant for something. Next week in Madrid, we are involved in the design and preparation of this international congress, Reuse Euromed. There are many interesting keynote speakers, several works that have been presented to this meeting, and only share with you this information. Maybe that someone could be interested in participate. Is on time. Thank you, Jorge, for your collaboration. I finish.
Not at all. 1 moment. I'm going to repeat math. Thank you, Javier. Yeah. Good morning, everyone. Before I begin, I would like to thank the University of Navarra for inviting me to participate in the first SUSTAGRI Summer School. I'm going to continue with the second part of this presentation, focusing on the sensorization of irrigator project. We will now move on the location of the pilot site. My colleague Javier has spoken about this site. Yeah, we have locations of pilot sites in Spain, Portugal, and France, mainly and now in hops, vinegar, olive and tomato, almond, and olive. Here is the network architecture using an example of these nodes measuring soil water content and agroclimatologic station. This send the data via LoRa to a gateway, which finally at last it to a server using 4G modem. Yeah, here we have 6 nodes. Okay, all the nodes measure soil water content, soil temperature, air temperature, and relative air humidity. Send the node data to LoRa gateway, and LoRa gateway send the data to servers. Yeah. At the same time, we have in all pilot sites, we have a weather station that measure rainfall, air temperature, relative air humidity, wind speed, and solar radiation that send the data by using LoRa radio packets to the LoRa gateway, and after send this climatological data to servers. This is an example of the SIL pilot site, where you can see the 6 nodes in the hops graph and the location of the agroclimatological station. Here we have 6 nodes here. Yeah, these nodes here is the agrometeorological station. All the nodes and the agroclimatological station sends the data to a gateway that is it's here. Yeah? And this gateway sends the information to a server. Yeah. This slides outlines the key characteristic of the microprocessor used for the sensorization. It's a development board based on the ESP32, which comes with integrated LoRa data transmission and built-in screen and micro SD card data storage. Yeah? Here is the heart of the system. Yeah, we have a microcontroller ESP32. Yeah, little screen, SD card reader, and we have the possibility to send the data using LoRa transmission system. Yeah, this is the node sensors. In its node, it's possible to have the HT22 is a low sensor air temperature and relative humidity sensor. Yeah, it's a low cost sensor. We have two DS18B20 low cost soil temperature sensors. Here you are. And two DF robot low cost capacity salt water content sensors with analog output. Two Teros 12 sensors with a transmission protocol FDE12. This sensor measured soil water content, apparent soil electrical conductivity, and soil temperature. Two Teros 21. This sensor measure soil water potential. And finally, Flora Pulse, that it's a sensor that measures sealing water potential. Yeah, we have a lot of sensors. This is the first one are low-cost sensors, and the three last sensors are commercial sensors. This is here you can see a node installed in an olive tree in Carrion del Céspedes, Sevilla, Spain, alongside a schematic showing how the installation was performed. Here you can see what is the sensors, the capacity sensors and soil temperature sensors are in surface. And indeed, we have at 20 centimeters depth, we have Teros 12, another Teros 12 at 45 centimeters. And the same depth, we have Teros 21 to measure soil water potential. This is a picture about the installation of Teros 12. This is the PCB for the node, and this is the PCB for gateway to LoRa. This is a 4G modem with we use it to send the data to MySense platform. Yes, this is a description of the agrometeorological station sensors. We have SHT31 low-cost air temperature and relative humidity sensor. Yeah, we have Davis instrument solar radiation sensor, pianometer model 6450 with an spectral response from 400 to 1100 nanometers with analog output. We have a panoramic rain gauge with a 0.2 millimeters precision resolution that use a red switch. And finally, low-cost wind speed sensor is a pulse with pulse output. Yes, this is a picture of agroclimatological station. Yes, this is the radiation shield. Inside is the temperature or relative humidity sensor, wind speed sensor. Yes, the solar panel. Yes, rain gauge, and here our solar radiation sensor. This is the little screen which we can see the information. Yeah. This is the latest, this photograph displays the latest PCB version featuring connection for E2C communication sensors, analog measurement by the ADS 1115 chip. It supports 5 volts and 3.3 volt sensors, power, both continuous and switched alongside an RT and clock. Additionally, there is the possibility of connecting 4G modem equipped with a relay to control the power and time communication between the modem and the ESP32. It's carried out by a local Wi-Fi network. Yeah, here this is the ports E2C. This is the analogical digital analogical digital converter. Yeah, and this switch we can change at different voltage. 5 voltage and 3.3 voltage to supply energy to the different sensors. Yeah, LoRa good way. The function is to receive data from nodes and weather station and transmit it to a server using a 4G modem, while simultaneously storing it on a micro SD memory card. Here you can see memory card. Data is transmitted every 3 hours. If an issue occurs during data upload, this data is stored and sent during the next connection. All the data is stored here is the memory card. All is ESP32 programming is carried out using the Arduino IDE software, which is based in C++. We have a Arduino program called an sketch. All the code for programming the microcontroller is here. Yeah. Problems encountered in the situation of this project. As with all projects, there are always problems and difficulties. The main challenges were linked to the new PCB used in the agroclimatological station, and these issues were related to the ADS 1115 analog to digital converter chip. Yeah. And the integration of the pulse output anemometer. Here, the problem with this chip that this used to convert analog to digital signal is the sensor, the solar radiation sensor has a peak, a voltage peak that causes the burning out the chip. Yeah, we need to change to introduce a thinner diode to reduce this peak. Yeah, and the other question is we need to use auto coupler to convert the output, the push output from wind speed sensor to from around 12 volts to 3.3 volts. Finally, integration with the MySense platform. No? All data are uploaded to a server at University de Trás-os-Montes e Alto Douro in Portugal and managed by the MySense platform. We send this data. The platform MySense reads this file and transform in this graph. Here you can see an example. This example is for solar radiation measurement from a weather station. The data is in water in watts per square meters. Yeah, this is another sample with raw data with soil moisture sensor. We can see the graph typical of irrigation cycles. Small irrigation, irrigation, irrigation. Other examples of this technology's application outside the Erie Water project include using a Herbert capacity probe, like this one, which allows for the simultaneous measurement of soil water content at multiple depths, in this case at 10, 20, 13, and 40 centimeters. Another application will be the measurement of water quality parameter, as like pH measurement, pH measurement, electrical conductivity. We can use analog output, or R is 485 with Modbus protocol. It's possible with this technology use a lot of different types of sensors signals. Yeah. And finally, advantage and disadvantage of low-cost equipment. Yeah. Advantage: cost effectiveness. They allow the deployment of massive sensor networks and a fraction of the cost of scientific equipment. Yeah, it's very important to have a cheap equipment. Ease of integration. They are compatible with IoT, Internet of Things protocol, facilitating real-time data transmission via Wi-Fi or low-power networks such as LoRaWAN. In this case, we transmit the data from nodes to gateway using LoRa. Customization. They offer flexibility to connect a wide variety of sensors, humidity, temperature, CO2 conductivity, adapted to the specific sound and output data formats.
Okay.
Disadvantage? Yes?
No, go ahead, Jorge. Yes.
I am going to finish. Disadvantage and challenge. Lower accuracy and resolution of sensors. They tend to have a higher margin of error, reduced lifespan, and finally, the most important for me, learning curve. They require programming and electronics knowledge to assemble components, code, algorithms, and process raw data. This is, in my opinion, the main difficulty to use this technology, the learning curve. Thank you very much for listening. Does anyone have any question?